Hi everybody, this is me Ankita Menon, and today we are going to discuss our fifth video from surface chemistry titled Langmuir Adsorption Isotherm. Okay, so in the previous session, just a quick revision, we discussed about the Freundlich adsorption isotherm, and under which what we learned is the extent of adsorption is going to be equal to Kp to the power 1 by n, where the value of 1 by n is in the range of 0 to 1. If we take the logarithm of this particular equation, we get log of theta is equal to log of k plus 1 by n log p. This is where we stopped our previous session with one or two questions as well. Now today, we'll be discussing about another type of isotherm. So the first type of isotherm that we learned is Freundlich adsorption isotherm. Now the second type of adsorption isotherm that we are going to discuss is Langmuir adsorption isotherm. Now why was a need for another isotherm is because there are certain limitations. So please note down limitations of Freundlich adsorption isotherm. So the first one was, we know that there are two constants over here, K and N. These are called the Freundlich constants. So by the name constant, it means it should be the same, the value should be the same under all conditions, but it is not. Okay, so the first limitation was K and N, in brackets you can write supposed to be constants. Supposed to be constants. Okay, vary with temperature. So at different temperatures, they found that the value of K and N, the Freundlich constants, were different. One thing. The second thing was this equation of theta is equal to Kp to the power 1 by N. Okay, this was valid only for a very small range. Okay, so this was valid only for a small range of temperature. This was the second limitation. Okay, so whatever equations that we got from Freundlich adsorption isotherm, they were derived based on certain observations. And because it was, derived based on certain experimental observations, it had some limitations, and the two limitations are listed over here. And therefore, there was a need for another type of adsorption isotherm that would overcome the limitations of Freundlich adsorption isotherm. And that was Langmuir adsorption isotherm. Very important. Whatever exam you're preparing for, the most number of questions from surface chemistry has come from Langmuir adsorption isotherm. It's that important. So we'll be covering this in two parts. So let's begin. First of all, we need to learn the assumptions, the postulates. So there are certain statements regarding Langmuir adsorption isotherm. If you're lucky enough, you will get questions from these postulates itself. Okay, so the first question, the first postulate. The adsorbent surface, I'll explain. The adsorbent surface contains fixed number of active sites on which gaseous molecules can adsorb. Okay, which means, let's say you have a solid surface. If you have a solid surface, the gaseous molecules will occupy something called the active sites. And these active sites that are present inside the solid surface are fixed. For example, let's say this is a solid surface, and these circles that I am drawing correspond to the active sites of the adsorbent. So if you can see 3 into 6, 18 active sites are present over here, and hence it is fixed. The gaseous molecules will not occupy any of the interstitial positions. No random positions, only on the active sites. Okay. Now, next. So each of the adsorbent surface has got fixed number of active sites. And the next one is each active site can adsorb only one gaseous molecule. So we already know that if you consider physics option, multi-layer formation is possible because they are held together by very weak van der Waals forces. But according to Langmuir, what was proposed is each active site can occupy only a single gaseous molecule. So if it can occupy only a single gaseous molecule, then the adsorption would lead to monolayer formation. Adsorption is monolayer. Right? Because at each active site, you can see only one. So only one layer of gaseous molecules can be held, not more than that. Next. Now, when you see a gaseous molecule being adsorbed on a solid surface, we already know that this process is exothermic. And if this process is exothermic, you know that when a gaseous molecule adsorbs onto a surface, some amount of heat is liberated. So the enthalpy associated with this is negative. And this negative energy is always the same, which means, let's say, when the first gaseous molecule adsorbed onto the surface, the amount of energy which was liberated was minus x. The same amount of minus x will be liberated when another gaseous molecules come. Same over here, minus x. Over here as well, minus x. So irrespective of the position of the active site, corresponding to each gaseous molecule being adsorbed, there is a definite amount of heat which is being released. Okay, so that is the fourth postulate. Let's write it down. A fixed amount of heat called heat of adsorption is released when a site is occupied. That is because it is exothermic. We already know that. Additionally, this heat, this is important, this heat is identical. I think this was asked in 2011 or something, this postulate. This heat is identical for all adsorption sites. All the sites, whether it is from the edges, from the middle, from the corners, wherever it is, always the amount of heat which is released is going to be fixed when a gaseous molecule is adsorbed. Okay. Fifth postulate. The gaseous molecules do not interact with each other. The gaseous molecules do not interact with each other. I think that does not need any explanation. So if there is a gas moiety, which is being absorbed on the solid. The only attraction is between the gaseous molecule and the solid. There are no interactions between these two gaseous molecules. Okay. Sixth one, they are in dynamic equilibrium. They exist in dynamic equilibrium. So if they exist in dynamic equilibrium, it means you have a gaseous moiety on a solid surface. Forward reaction is adsorption. Backward is desorption. And it forms GS. Right? Now, from this, let's build and come to the equation of Langmuir adsorption. Now, we know that if it is under equilibrium, the rate of forward reaction is going to be equal to the rate of backward reaction. Right. Now, forward reaction means it is adsorption. Backward reaction means it is desorption. Now, from chemical kinetics, we already know how to write the rate expressions. Now, again, I'll be tagging the playlist of the chemical kinetics if you want to refer, and then if you want to read. Okay. So this is, let's say, for forward, the rate constant is Ka, and for backward, let's say it is Kd. So at equilibrium, for the forward process, we know Ka is the rate constant for adsorption into concentration of the reactants G into S. And for the backward, it is rate constant for the desorption, and desorption happens to GS. GS. This is how it is. Now, pay attention. The concentration of the gas is usually notated by P. Correct? Because that is the pressure of the gas, and you can write, instead of G, you can write it as P, which is the pressure of the gas. Okay. Now, S and GS, how are you going to represent? Now, understand that GS, for example, if you consider this particular diagram, there are 18 active sites. There are 18 active sites, and out of which 1, 2, 3, 4, 5 is occupied. Correct? So the occupied site, so theta, if you have to write, is the number of occupied site, which is 5, divided by the total number of sites, 18. That's it. Okay? So theta is equal to 5 by 18. How did we get that? Total number of active sites 18, and out of which this GS complex is formed at 5 positions. Right? So theta is 5 by 18. Now, how many vacant S or how many vacant substrate active sites are present? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Or the way you can find it out is the vacant substrate is equal to 1 minus theta. Right? So over here, the substrate concentration can be written as 1 minus theta. This is equal to Kd, and Gs can be written as the surface coverage, theta. Now, if I'm going to rearrange, so I'll bring this Kd to this side. Ka by Kd into P is equal to theta by 1 minus theta. And this ratio of the forward rate constant by backward rate constant is capital K, which is a Langmuir constant, So I can rearrange and write it as Langmuir constant into the pressure of the gas is theta divided by 1 minus theta. I hope all the parameters are known to you. K is the Langmuir constant. P is the pressure of the gas. Theta is the extent of adsorption. Okay, that is theta is equal to number of occupied sites divided by total number of sites, total number of active sites. Okay, so this equation corresponds to the Langmuir adsorption isotherm. So you call it Langmuir's constant, you can call it equilibrium constant. Okay, so in questions you will get different, you can also call it as Langmuir distribution coefficient. So a lot of types of wordings are used in the exam. You have to understand that corresponds to the scale. Yeah, so this is the first form of the equation that you should know. Kp is equal to theta by 1 minus theta. Now from this we can rearrange and come to another form. Kp is equal to theta by 1 minus theta. Very easy. This corresponds to Langmuir adsorption isotherm. In the previous video, what we discussed is Kp to the power 1 by n is equal to theta. This was Freundlich. Okay, so please don't get confused. All right. Now the same equation I'm going to rearrange and I'm going to write it in terms of theta. What am I going to do? I'm going to cross multiply. So if I cross multiply, Kp into 1 minus theta is equal to theta. Opening the brackets, Kp minus Kp theta is equal to theta. Bringing theta terms to one side, Kp is equal to theta is common, taking it outside 1 plus Kp. Or theta is equal to Kp by 1 plus Kp. So this is our equation number 1 and this is our equation number 2 of Langmuir adsorption isotherm. Both are very important. Both of these are very important equations. Okay. Now understand that over here, theta is something that has not got any units. Correct? This is the number of active sites divided by total number. So this has no unit. So on the right hand side also, you should get something that has got no unit. Correct. Now on the top, we have got pressure. Pressure can be in terms of bar. It can be ATM. And you are multiplying it with something and you don't know the unit of that. But on the left, what you need is dimensionless, no unit. So by this logically, if you understand the value or the unit of K, unit of the Langmuir constant is going to be pressure inverse. Is going to be pressure inverse. Okay, so that's it. That's about Langmuir adsorption isotherm. So we discussed about the different postulates, very easy peasy ones, and two equations. Kp is equal to theta by 1 minus theta and theta is equal to Kp by 1 plus Kp. Now, based on this, let's come up with certain graphical representations. Write down the heading, graphical representations. Graphical representations. So the equation that we are going to take is theta is equal to Kp by 1 plus Kp. This is the equation that we are going to take. Case 1. We are going to assume that the pressure is very low. We are going to assume that the pressure is very low. So if the pressure of the gas is very low, so whenever such conditions are applied, we know that it is always applied at the denominators. So at the denominator, if P value is very low, Kp value will also be very low. If Kp value is very low, the value of Kp in comparison to 1 will be very low. And hence this equation as a whole becomes theta is equal to Kp. Why? Because you neglected the value of Kp and what you have is Kp by 1. So this is the equation. This is the equation. Now corresponding to this equation, if we have to plot isotherm, right? Isotherm is always surface coverage versus pressure at constant temperature. Theta versus P is linear. It has got a slope of K and hence it is going to be a straight line. It's going to be a straight line. So how did we get this equation? That was because P is very low. If P is very low means the value of Kp will also be very low. So you will apply this condition at the denominators. If Kp is very low, we'll assume that it can be neglected. This can be neglected in comparison to 1. Okay, that is what we do. All right. Next condition, case 2, is if P is very high. So if P is very high, what does that mean? So if P is very high, automatically the product of Kp will also be very high. Then in comparison to the other term at the denominator, the value of Kp will be very high and hence this 1 can be neglected because now Kp is very high. So you neglect 1. So what do you get? Kp by Kp. So you get theta is equal to Kp by Kp, which is equal to 1. See, you're getting 1. So now if you plot theta versus P at very high pressures, theta is equal to 1. So this value over here is 1. It's a constant. Now case 3 is at moderate pressures. If pressures are moderate. If pressures are moderate. Now, if pressures are moderate, what do we get? You will be getting a combination of these. So from this, if I have to write the order of the reaction, which depends on P, see here, theta is proportional to P to the power 1 and hence the order of the process at very low pressures is 1. Here, I'm getting 1 and 1 can be written as theta is equal to P to the power 0, correct? Any number raised to 0 is 1. So, order over here is 0. So, if I compare, if my pressures are low, my order of the reaction is 1. And if my pressures are high, my order of the reaction is 0. Now, if the pressures are moderate, what will happen if the pressures are moderate? The order of the reaction that you will be getting would be between 0 and 1 and hence you can write it as it is fractional. It is going to be fractional, right? So if I combine both case 1 and 2 and in reality, how does the plot look like? So you have theta versus P at very low pressures. See? At very low pressures, it is linear and at very high pressures, it is constant. So if I combine these two, at very low pressures, it is linear and at very high pressures, it is constant. Now, if I connect these two, this is how we get. That's it. So here, the order is equal to 1. Why? Because in this region, the pressures are low. Correct? This corresponds to low pressure. And here the order is equal to 0. Why? Because the pressures are high. This corresponds to high pressure. And in between you have fractional order. So this is the combined graph, the actual graph. If you just revise and go to the session where we discussed between isotherm, isobar and isostern, there I had mentioned that you will be understanding it better. See, this is a session where we discussed about adsorption isotherm and we drew something like this with a plate tube. And I mentioned that this is attaining a plateau because of the saturation. Why? Because the pressures are so high that the theta has now attained a constant value. I hope now you have got a better understanding of that plot. Okay, so this is how it looks. Now, there are certain other ways in which you can write the expression of Langmuir adsorption isotherm as well. So I'm going to explain that. Now, based on the volume, you please write it up, VAD. VAD is the volume of gas adsorbed at time t. I'll explain what that is. And Vm is the volume of gas for monolayer formation. Okay. Now, we already know that theta is equal to Kp by 1 plus Kp from the earlier derivations. Now, I'm going to write this in terms of VAD and Vm. So, we already know that theta is equal to number of occupied sites divided by total number of sites. Total number of sites. Now, if you have a solid surface, and in the solid surface, if all the active sites are occupied, that will form a monolayer. And if that forms a monolayer, the volume of the gas which is required to completely cover is going to be Vm, correct? So I can write that total sites can be equated to the volume required to form the monolayer. The total number of sites in number can be similar to Vm. Why? Because monolayer volume is the volume of the gas which is required to completely cover the whole solid surface. Okay. Now, in certain cases, the whole of the solid surface may not be occupied. May not be occupied. If not, let's say there are only two gaseous molecules which are being absorbed. So if there are only two gaseous molecules that are absorbed, then corresponding to these two gaseous molecules, there will be some volume. So for example, Vm is, let's say, is 100 centimeter cube. That means 100 centimeter cube of the volume of the gas is required to completely cover the surface. And when you have just two moieties, the volume corresponding to the two moieties is 10. Okay, so I can write the extent of adsorption as 10 by 100, which is equal to 0.1. Or I can write it as VAD, which is the volume corresponding to the gases which are already adsorbed. And I can write it as VAD by Vm is equal to theta. I hope that is understood. Okay. So, theta can be written as VAD by Vm. Theta is already known to be Kp by 1 plus Kp. If not, if so, let's plot between these two. What I'm going to do, listen very carefully. You can write down the heading 1 by V versus 1 by P. That is the plot that we are going to discuss. 1 by V versus 1 by P. So by now, you know that theta is equal to volume of the gas adsorbed divided by the total volume of the gas required to form the monolayer equal to Kp by 1 plus Kp. Let's take the reciprocal. So if you take the reciprocal, now I'm going to consider only these two. Vm by VAD is equal to 1 plus Kp by Kp. Okay? Now I can write it as Vm by VAD is equal to 1 by Kp plus Kp by Kp is 1. Now I'm bringing Vm to the other side, or I'm going to divide the whole equation by Vm. So what will happen? See, Vm is going to be a constant because that is the volume which is required to form the constant layer, a monolayer. So then it is going to be 1 by VAD is equal to 1 by KPVM plus 1 by Vm. And our purpose is to plot a graph between 1 by V versus 1 by P. So see, 1 by V is already there on the left, and 1 by P is what you need along the X. So if this is my Y-axis, if this is my X-axis, now you clearly know this is of the form of a straight line. I'll rearrange so that you can understand. 1 by VAD is equal to 1 by KVM into 1 by P plus 1 by VM. So see, this is your y-axis, this is your x-axis, and this is of the form y is equal to mx plus c, right? So you have got a straight line, and out of the straight line, the slope of the line is going to be 1 by kvm, and the intercept is going to be 1 by vm. Very easy. Okay. This is another equation. So this is equation number 3. And finally, there is one more equation that you want, which is P by V versus P. So the same equation 3, you just multiply it with P. That's all. You just multiply it with P, and let's see what happens. So when you multiply it with P, you get P by VAD is equal to 1 by KVM plus P by VM. You need to plot between P by VAD. Yeah, okay. P by VAD versus P is what you have to plot. So P by VAD is your y-axis, 1 by KVM plus 1 by VM into P. Now see, this is your x-axis. This is your y-axis, and this is of the form y. This is going to be your m, this is your x, and this is your slope. Again, you will get a straight line whose intercept is going to be 1 by kvm, and whose slope is going to be 1 by vm. Okay, so please don't get confused, because in the earlier case, the intercept was 1 by Vm and the slope was 1 by KVM. Here it is just the ulta. The intercept is 1 by KVM and the slope is 1 by Vm. So please pay attention. Summarize all the equations that we learned today. So this is equation number 4 of the day. Make a chart. I'll be again summarizing all these equations in the next session, where we will be discussing about the second part of Langmuir adsorption, and we'll be doing some problems as well. Okay, so with that, we wind up the session. See you in the next video. Bye-bye.